Welcome back. We will continue our discussion on the atomic force microscope. This is the third lecture on AFM. In the previous lecture, towards the end of the lecture, we discussed about the different major components of an AFM, which we are going to sort of discuss in somewhat greater detail, and some critical operational aspects, which will give you an even better idea about the working of an AFM. So, I will just recap on that. Of course, we have now understood that we need sharp probes, but unlike an STM, the probes are not standalone and they have to be mounted on a cantilever, the purpose of which I just briefly mentioned that the purpose of this cantilever is essentially to track the variation of the interaction forces, but how it is actually or exactly done is requires a little bit of more discussion, which we will do. Then we have a photo detector with a laser source. In fact, you see the laser falls here, it somehow gets reflected. So, it seems that these two are optically coupled through the tip of the cantilever, and that is in fact the situation. How to do that coupling is actually alignment, that is an operational aspect that I will discuss. Then this tip is mounted on a piezo scanner which scans, and then of course, you have a feedback control module. So, with this introduction, let us start. I mean, so this is another cartoon that sort of gives you in somewhat greater detail the major components. So, you can see, you can correlate with the previous slide. Here is the piezo scanner to which the cantilever or the tip is mounted. In reality, it is not exactly so like this. The cantilever is too small, it is maybe a millimeter or 2 millimeters or maybe even smaller than that, few hundred micron. So, that is, so actually the geometry is that this is the cantilever, it is mounted to a macroscopic chip, and this is about 5 or maybe 10 centimeter, 10 millimeter wide, I am sorry, and this is mounted on the AFM cantilever holder, as it is called, and this is very, very small. So, this may be about 500 micron, and this is tip diameter is of the order of a few tens of nanometer at best. So, anyway, the major purpose, major reality that for our understanding, we can assume that the cantilever is mounted to the piezo scanner. Then you have this laser source and the photo detector. In fact, it is called a quadrant photodiode, as we will see soon, QPD, and you have a feedback controller, and this is in fact this is the scanner, piezo scanner, and this is the sample. There were earlier designs where the scanner, the rastering, XY rastering used to be done at the substrate, and the Z control was done by the piezo mounting, but now the models include a cylindrical piezo and everything is done roughly by the scanner. So, moving on, the probes or tips, the most important thing, you can see this is a real life SEM image of what I told. So, this is the cantilever. This is typically made with silicon nitride or silicon. Silicon nitride probes are very common. So, this is that every instrument it varies. So, this is one of the probe mounts. Here that so called chip will fit in like this, and the cantilever will be like this. So, that is what you see, this is the tip in fact, and at the edge of the tip is very sharp. This is typically radius of curvature is 10 to 20 nanometer. Again, I will repeat, I have briefly mentioned why you need a very sharp tip. It has nothing to do with the tunneling current, like why the sharpness of an STM tip is required. However, if you take a very blunt tip, please do not forget, and you will soon realize that the minimum resolution you can achieve is strongly dependent by the radius of curvature of the tip, right. So, if you have a blunt tip, your radius of your lateral resolution will decrease. So, here are some details. Tip diameter 15 to 25 nanometer, resolution is a function of tip size. Cantilever behaves like a spring, and in fact, there is one mode, the intermittent contact or the tapping mode, as it is popularly called, where the spring property is extensively utilized. Its stiffness is critical. This also I have mentioned, because you would like to take a cantilever that is flexible or malleable enough that it deforms to the van der Waals forces with the surface. You do not want to make it take a very rigid cantilever which does not deform, because that does not serve your purpose. So, a good cantilever is measures small, spring constant should be as small as possible, stiff cantilever will not respond. Resonance frequency, this is important, it should be in this range. Resonance frequency you need in one of the modes, we will discuss. The base tips have a radius of curvature of around 5 nanometer, but many of the commercial tips one uses have radius of curvature of 10 to 20 nanometer, because please understand that fabricating tips with this small size itself is a major microfabrication challenge, and therefore tips are very expensive, and smaller or sharper radius of curvature at the tip edge you would like to have, more expensive your tips will be. Modes of operation we will discuss later, this has nothing to do with tip, but there are primarily two modes, contact mode and non-contact mode, or the intermittent contact mode. And anyway, so these are some real life pictures of an AFM, but this again varies from instrument to instrument. You tend to get a feeling that there is some microscope like thing, in fact it is an optical microscope, it is not related to the atomic force microscope. The real AFM is only this much, it is a small device, in fact everything what you see is sort of, other than the controller, is embedded in over here, that is again not a big deal. So, we have already talked about the tip and the cantilever. Next we focus our attention in the so called photodetector or the photodiode. So, what we have, what is a photodiode? In fact, if you shine light on a diode, a type of diode over which if you shine light it will generate some voltage, that is why it is called a photodiode. So, what in a commercial AFM what is used is not only a photodiode, but it goes by the name position sensitive photodetector, or often it is called the quadrant photodiode. So, what it means is that depending on where the light falls, the magnitude of the voltage generated is going to be different. Typically the range is 0 to 10 millivolt, and if light is shined at the center it is 0 millivolt, if it falls at the periphery it is 10 millivolt. However, more importantly, even if let us say these 2 points fall on the same circle, that is the total voltage is same, the position sensitive diode can sort of identify the difference in the positions, that is the coordinates you can say, that is why it is called quadrant photodiode or split photodiode or whatever, PSD also, position sensitive diode. So, though let us put it like both of these lines lie on the 4 millivolt line, the x and y coordinates here and here, obviously like a graph paper, they are going to be different, and the QPD can identify that. It is good to know these things. I mean, if you are really doing research on an atomic force microscope, you can maneuver these things to achieve or extract more data, but even if you do not understand so much, it is good to know how it actually works. For our understanding, this much is sort of enough. This QPD will be in fact used to track the displacement or the deflection of the cantilever, as you can see here, but how we will talk about it in few minutes time. What is important to realize that in the context of this QPD, it is able, let us say, to track if the reflected light was initially falling here and after some deflection it has now shifted to this position. This is very important. In fact, if you remember our basic understanding of how an STM works, a scanning probe microscope always requires an error, particularly with a feedback loop, so that the feedback loop can be activated at every point, and you can get back to something that was set at the beginning of the scan, that is the set point. So, what is the error in case when you are trying to measure the forces? And I am giving you a clue. In fact, the error is generated on the quadrant photodiode. What exactly is the error, you will soon understand once I talk about alignment and approach. So, this is the QPD. Now, you see amongst all the instrument major components, we have not talked about the piezo, but you know that is the piezo scanner, but you see you know that we have already talked that a piezo scanner, a piezoelectric material is something to which if you apply a voltage, it can change its dimension, or if you forcibly change its dimension, it will generate some voltage. So, here we in fact we apply a voltage, and that voltage how it comes, that voltage in fact comes from the feedback loop. How that error voltage gets generated, you will understand soon. So, amongst these major components, we have talked about the photo detector. Of course, there is a laser source, we have not talked much about it. Feedback controller, simply we will not talk much, because it just feeds the error and adjusts the piezo scanner. We will talk about the scanner shortly. So, let us see, here we have that laser source from which laser light is coming, and here we have the cantilever and the tip. Only one thing I briefly mentioned in one of the initial lectures, but I forgot to tell in detail, that this is the typical geometry of a cantilever. Here it has a tip. Additionally, on the reverse side of where the tip is made, a shiny coating, a reflective coating is given. It is not working. So, let me see what I can do. Sorry, it is turning out to be black. Let us see. Yeah. So, over this area you have a shiny coating. What is the purpose? Anything shining tend to reflect light, at yes, in fact this acts like a micro mirror. So, that is exactly what you see here. Just one second. That is what you see here. The cantilever sort of has a gray coating. This is in fact the surface coating. So, now what we are going to talk is the process of alignment, and what alignment does is you will now realize that this in fact couples, optically couples the cantilever and the laser source and the QPD, right. So, this is what it does. So, what you have a cantilever mounting where you have two screws which you can rotate in x and y direction, that is all, and you have this QPD which also comes with two screws which you can rotate in again in x and y direction. So, it is roughly like you have a laser source coming from here, right, you have a laser source coming from here, and you have a QPD somewhere over here which you can move up and down in this particular plane, and you have the cantilever somewhere over here. I told the laser is falling from here, which again you can move back and forth in this particular direction. So, what you first do, see the laser light is falling from the laser source, you have your cantilever, first you have to mount your cantilever to the cantilever holder, then you start turning those screws, these two screws, the x and y screws, and in the process what you do is, so this is the reflective coating we have already talked about, and you are now turning, and your objective, so laser light is going in this direction, light is simply going in this direction, and your objective is to somehow bring this cantilever into the path of the laser, and this is what you do. The moment you do that, what starts to happen, since it has a shiny coating, laser light now starts to reflect out from the tip. It reflects from the location opposite of which the tip exists. Is it clear? I think I will sort of repeat this step. So, you have this laser source, you have this tip mounted onto the tip holder, then what you do, you in fact rotate these two screws, the x and y screw, in such a way that the cantilever is shifted and it now lies in the optical path of the laser, right. And the moment it goes to the optical path of the laser, since it has a reflective coating over here, the laser light gets reflected. So, in fact, laser light which was initially going in this direction does not go in that direction anymore. So, this is only part of the alignment has been achieved. Now, what is the next thing to do? The next thing to do is you again rotate the, now you rotate the screws, the X and Y screws of the photodiode in such a way that you can move the photodiode and again bring it to the path of the reflected laser light. You want to bring the photodiode. So, it is like this, laser light is now reflecting like this. So, you have the photodiode which might be skewed. So, you do something, you rotate it in X and Y in such a way that it goes and the laser light falls at the center of the photodiode. So, that is exactly what you do here. You sort of move these two screws and your controls are minimal. In fact, that is something you need to know, that you just have these X and Y screws, you rotate it and the photodiode sort of goes into the path of the reflected laser light, and you do it in such a way that it falls, the reflected light falls at the center. What did I mention about light falling at the center of the QPD? That would lead to a 0 voltage, and this is when alignment is complete. So, what have you done? In fact, you have now optically coupled the laser source and the photodiode, optically coupled the laser source the cantilever and the photodiode. This process of coupling these three is called alignment. This is, I must admit that I am giving you a completely operator's perspective. I mean, if you want to really, this is not really related to the science of an atomic force microscope, but if you want to run the AFM, you need to know these things, and I find it extremely interesting. Honestly speaking, all you have at your disposal is two sets of screws which allows you to move the cantilever as well as the photodiode along one particular plane, and therefore, this step, the process of alignment, requires some bit of operator skill. There are modern day instruments which does automatic alignment, and many people tend to prefer those, because trust me, this is not the easiest of the thing. You are trying to bring in something in the path of a laser light, which I said that this entire portion is few hundred micron. So, it is indeed small, it is not that easy, but you talk to any experienced AFM operator or somebody who has been working with the atomic force microscope for a significantly long period, he or she will immediately tell you that they will prefer a manual alignment, because that is where you really know. Because if you look very carefully, manual alignment really allows you to identify whether your laser is falling here or it's falling here, and that affects image quality, you trust me, right. So, I have about 10 years of hands-on experience, so maybe more than that with the atomic force microscope. So, with that I tell, but anyway, this is the process of alignment. So, once the AFM is aligned, in fact, it is fine. So, reading is now 0 volt, which is okay, and then we would have done all this, but anyway our objective is to scan the surface. But whatever I have discussed so far, that is alignment, where these three components get coupled, we have not talked about the surface yet. So, what is the next step? Now, you sort of couple the surface with this assembly, so that your AFM is ready to scan, and this particular process is also very important. It involves very easy but very subtle science, and we will talk that in sort of detail, is known as approach, and that is what is the next thing we are going to talk about. So, what is approach? And approach in fact relies fully on the concept of interaction of van der Waals forces between two surfaces. So, let us see what it is. As I said that when you initially align the cantilever, the surface is far away, right. The surface has no effect. In fact, you would like to align far away from the surface, because you are moving the cantilever abruptly with your hand and you do not want the cantilever to crash on the surface. That is why alignment is done far away from the surface. But now, I would also like you to look carefully to this image and to look at two aspects. The laser light is falling at the center, which is something, or you can look into here, because this is getting truncated in some of the screens. This is the first configuration, configuration 1. Tip is like this. What you note is that laser light is falling at the center, which is fine, but you see that I have given another tiny blue spot. Can anyone guess what is that spot? It will be clear to all of you very soon. So, now what we do this, so this cantilever is mounted to the piezo scanner, and there is in fact a stepper motor which is now going to bring the surface close to the cantilever tip, so that they come in contact, and now the system, the instrument is ready to scan. Now, question to ask is, when you are engaging the stepper motor, how much does it bring, how close does it bring the surface, and that in fact is determined by the deflection of this cantilever itself. So, I will just draw or highlight this condition at the QPD in bit detail. So, all of you now understand that right after alignment, the laser light is falling at the center. Sorry, the picture is not very good, but right after alignment, laser light is falling at the center and reading is 0 volt or 0 millivolt. Okay. But somewhere this is, here is your cantilever, this is your tip. So, laser reflects, laser is coming from the laser source, it gets reflected and it falls at the center. Okay. Now, what is being done? So, initially when you do this alignment, the surface, the sample was far away. So, there was no interaction, and I would redraw something that we talked in greater detail in the initial class, and you should be able to identify it immediately now. This is in fact the Lennard-Jones potential. I told you one thing, and that is something again I am going to tell you in one of the subsequent classes when I talk about instability, that van der Waals interaction scales as 1 by r to the power 6 between two particles, fundamental particles. But when you talk about the interaction between two surfaces, it actually does not scale as 1 by r to the power 6, it scales as 1 by r square. But if you look into, so AFM, in fact you would see that we are talking about the interaction between the tip and a surface. The tip is sharp, but still the radius of curvature of the tip is 10 to 20 nanometer. Typical size of an inorganic molecule is about an angstrom. So, considering that the tip has about 100 to few hundreds of molecules. So, one way of considering that well, the tip is also a surface. So, one can look into the interaction as the interaction between two surfaces, but let me also tell you, many people consider the interaction between the tip and a surface to be governed by the pure Elja potential, that is 1 by r to the power 6. Anyway, the nature of the interaction remains same, and probably it is a fact that the scaling is more than 1 by r to the power 6. So, I am running bit out of time. So, I think in the next class I will talk about the issues related to approach in greater detail. So, approach essentially is bringing the sample in proximity with the tip, so that your AFM is now ready to scan, and most instruments excepting few in fact have an interlock that as long as the AFM tip has not approached the sample surface, the piezo scanner will not get activated. So, this approach is not governed by piezo, because you actually would like to bridge a reasonably large gap between this configuration, let us say, where you have done your alignment and your surface. In fact, it is possible, and many times you actually do that. You first align your cantilever, you align your instrument, then only you mount your sample. That is also possible. So, the rule of the thumb is that you align when the sample is not there, because you do not want to have any spurious reflection coming from the sample, and then once the instrument is fully aligned, then you engage your sample and then you bring it close to it. And that process of bringing the sample close to the AFM tip is known as approach, and I will pick up the discussion from approach in the next lecture. Thank you.